All right, so before I start, today's topic will be on power spectrum of stochastic processes. And before I start, let me give you a common problem that here is a Gaussian density function. So I'm going to call it f1x. You can see it looks like Gaussian. Here is some other density function. Think of this as due to signal, and think of this is some sort of contamination, some random variable. But you can think of noise, but I'm going to call it f2x in the two density functions. Of course, if signal and noise are added, remember, if I call this to be x, you know the density function of x. That's going to be, let's assume these two are independent, so that's going to be the convolution of x with the convolution of knowledge, with the noise density function. You get some new density function. But I want to look at something else. Sometimes the density function is contaminated. What that means is it's like maybe salt and pepper noise. It's just that here the signals are getting added, signal and noise, where here, consider a case where 99% of the time it is this density function, but 1% of the time it is f2. So you consider a new density function, which is epsilon multiplied by, like this. Remember, this is something we have, this is not a convolution or anything. I'm just creating a new density function from the old density function, the way the kids will do, just add it up. Epsilon is, let's say, 98%. This is 2%. So if you pictorially draw this, and if this density function is like this, it's a density function. If you pictorially draw this, originally it was Gaussian, this is going to be slightly corrupted. This is a density function because you can see it's a non-negative function, and it is very quick to see that. You check it out. I'm not going to do this completely for you. I'll tell you what the problems are. So I'm going to leave you an exercise for you. So sometimes this happens. When you call this to be contaminated. So if this is Gaussian, suppose this is some mean and variance, then this is called contaminated Gaussian. So remember, this is not adding signal and noise. It's just corrupting the density function and making a new density function. So what is the question? Let's say, remember, we started with two density functions. Let's say this as mean and variance mu1 and sigma 1 squared. This is mean and variance mu2 and sigma 2 squared. So I'm going to call this, of course, if there is a density function, there is some random variable x. So f1 has mean mu1 sigma 1 squared. The density function f2x has mean mu2 and sigma 2 squared. So your problem is find the mean and variance. So x is, remember, x is this random variable created this way. So what I want you to do is find the variance of x. See whether you can do it. You should be able to do it. Obviously, I want it in terms of these four quantities and epsilon. So that's just a probability problem, simple problem. This will come up in image processing and so on, where you have a contaminated Gaussian. In other words, another way you look at this is data is 99% of the time, data is Gaussian, and once in a while the data may come from something else. This is unlike anything we have studied. I am not adding signal and noise. So what it says is that most of the time the data is coming from a Gaussian distribution. But you can think of the weather. Most of the time the weather is normal. So if you take a density over a long period, but once in a while there will be a tornado or something with a completely different density function. So if you want to have resources for the whole year, or if you're thinking about climate change and so on, so the whole point is the mean of this may be, because of this, what is the change in variance and so on. So the mean and variance, what it is, etc. So you can see for some certain models, this would make sense. Of course, you can keep adding also. In other words, you could say that I have a X density function, which is, let's say 90% of the time it is from this F1, but a lot of other times it is epsilon k over k fkx. So this epsilon k is, if you add up all these epsilon k's, that's 1 minus epsilon, the remaining portion. So you have many of them. Then you can try to find the mean and variance of the new random variable. So what you want to see is, if you call the variance of this to be sigma squared, how does it compare with the sigma 1 squared? This is the most dominant component. So you can see for climate analysis and so on, and this is the actual. So usually people will make predictions based on this component because this is all you will see. But once in a while, tornadoes and this and that will disrupt whatever is going on. So the question is, how big is this? Same thing with the mean. How large is the mean or different is the mean compared to this? This is like in stock market. Most of the time you assume you're a natural market, but what is going on now is one of these extreme behavior, right? That just gets here for about 1 month. So this is about 10%. You have this completely crazy density function, which is governing the data that's coming these days. So the data you collect could be coming from here 11 months, but it is coming from here 1 month, etc. So you can use this model many ways. You can do a thesis on it or do some work on it. But in any case, do the simple thing first. Find the variance of X. So it's just a warm-up problem for you from probability. And if you do this, this problem is good enough. You can it could come up in a mini test, for example, so maybe for the final exam. So something like this or variation of this. In any case, you should remember you can actually add two density functions. Take the average. That's a new density function, or take some percentage of each, and you get a new density function. So you have a new random variable. This is neither this nor that. That's the interesting thing. This X is neither this random variable nor that one. And X is not a sum of signal plus noise. And so it's a completely different funny form. So the question is, what's the mean and variance of X? As I said, you can use this for example, in TV or image, streaming TV, most of the time everything is normal, but once in a while you will see the streaks and data loss, this and that. So if you want to compute, or like electricity supply, most of the time it's a well-behaved distribution, but when you have power outs and this and that, it's there will be loss of revenue, so you want to find out what will be the overall behavior of this random variable. Anyway, many models are there possible. So let me move on with, so this is the problem. I just made a simple problem. Find the mean and variance of X, which corresponds to Fx. All right, so let me go to the main topic of today's problem. Is the power spectrum of stochastic processes. So remember, a stochastic process is a collection of waveforms. And in electrical engineering, with the two variables, the realization here and time here. So it's a collection of waveforms, each of them depending on some random quantity. In other words, you can think of it as a realization due to some random some game being played. Whatever is the outcome, depending on that, you get a waveform rather than a whole just a number. But of course, if you look at any time instant, you see a random variable. Another time instant, you see another random variable. Their cross correlation x1 of t, that is xt1, xt2, is what we call the autocorrelation function, t1 comma t2. If this is a function of t1 and t2, this is not stationary in any sense. If this is a function of t1 minus t2 and the mean is a constant, then we call the process to be Whiteson stationary. So the question, of course, we know any waveform has got energy and power. What is the distribution of it with respect to frequency, since that's the business we are in. And that's what we are going to look at today. Any questions? So, anyone? So since you are familiar with, since you know hopefully these notions through for a deterministic signal, where the Fourier transform is the key there, I am going to sort of go along those lines. So first of all, maybe we will do this Saturday or Sunday. You should review your Fourier transforms. I'm not going to do a complete review now. But if you have any signal, f of t, of course its energy is minus infinity to plus infinity ft squared dt. This is in time domain, right? This is time. That's the energy. Energy is, of course, a positive quantity. Question is, how do you, what is the distribution of this energy in the frequency domain? So that's where the Fourier transform helps. So Fourier transform, as you know, is ft e to the power minus j omega t dt. So we are integrating out t and we'll get a function of omega. This could be complex because of this j here. But so a Parseval's relation is, this is the key relation. If you integrate the this function under all
excuse
omega.
me, Professor?
Yeah.
You're starting to write off the screen.
Yeah, you're right. So this is my, that's good, right? Can
That's
you see
good,
it?
thank you.
All right, so this is Parseval's relation. I hope you know this. Now, I have a full video on all the Fourier transform, so you should review that. Or I don't remember, maybe this is Bessel or Parseval, I think. So notice that this quantity is, so this is the square, the area under the square of the function, either in the omega domain or time domain are equal, but time domain it is energy. So that means if you could plot this f omega squared as a function of omega, we know that this is the whole energy. So you get the energy distribution with respect to frequency by this picture. So for example, we know there is so much energy here, etc. So the question is, how do we, this is for a regular signal. How do we do, and stochastic process, the problem is you have so many realizations, so you can't just take the Fourier transform of what, which waveform will you take, etc. So you can see if at all you define power, you have to define it as a stochastic ensemble of, or average over all these realizations. Remember, there are many realizations, right? So whatever we do, so question is how to describe, how to characterize power versus the frequency relations, etc. That's our problem today. So we get some motivation from here, and so the yeah, maybe there's a 2 pi here, 1 over 2 pi here, but that's okay. It's a constant. So, so if you plot this quantity, this will, so for somewhere if it is very small, that means the energy here must be 0. And if this is very large here, that means a lot of energy is here, etc. This total thing is the energy here. So, so the sort of to keeping this in mind, and we know we have many realizations, etc. I am going to, so remember, a stochastic process actually goes on forever, especially if it is stationary. If it is a stationary process, you can't have it from somewhere to somewhere alone, because remember, translation in time should keep the. So this is a stochastic process, many realizations. So I'm just going to, for the time being, I'm going to look at this window of 2t. Let me see. So I'm going to do a Fourier transform based on, let's say, any one waveform over this duration. For the time being, I'm essentially trying to do something like this. So I'm going to do minus t to t, x of t e raised to minus j omega t dt. So you may say, so remember, this looks like x of omega. To remind that I've used only a small segment, I'm going to put a t here. So if you look at here, so this is certainly the Fourier transform of this one realization based on the data from minus t to t, like here. But whereas here we have used all the data, minus infinity to plus infinity, and this is the Fourier transform, and the energy is represented by the square magnitude. So I'm going to square this also. I'm going to square this quantity. Remember, this is a random variable because this is a stochastic process. This integration is like summation. Integration is like summation. So this is like scaling. So you are scaling and adding random variables. So this is a new random variable squared. So from here, this represents the energy distribution, right? Because the square is from any frequency to give you part of the energy within that frequencies. Here, what I'm going to do is, I'm also going to, what makes sense, as you will see, is rather than the energy, I'm going to look at the power. So I'm going to divide that by 2t. Remember, 2t because I've used the time duration minus t to t. And remember, as I said, this is only based on one waveform. So what I'm going to do is I'm also going to do expected value of this quantity. So I should do, of course, expected value on the other side. So let's see how much we can simplify this to. And then the ultimate thing I will do is I'll push this t to infinity on both the ways. That way I take care of all the waveforms. I hope you see what I am trying to do. So I'll do it here. So xt of omega is minus t to t, x of t e raised to minus j omega t dt. First I'm going to square it. I'll square it. Then I'll divide by 2t. That way I get the power, because this is the energy. Energy divided by time is the power, instantaneous power. Then I'm going to look at the average power by doing this expected value. So this is also expected value of this. So let's, I'm going to call this quantity Pt of omega. This is a Pt of omega, because this is, the quantity on the left is now a deterministic number, because the expectation removes all the stochastic aspect. Remember, expectation means we are doing the averaging in this direction by multiplying by the density function, etc. So let's open this up. So this is 1 over 2t, expected value. There are two integrals, minus t to t, x of t1, e raised to minus j omega t1 dt1, and then multiplied by minus t to t, x of t2 e raised to minus j omega t2 dt. So I'm going to take the star here. So I can write this as 1 over 2t, expected value of double integral minus t to t minus t to t. So notice the expected value, I'm going to put it here. So this is xt1, this is xt2 star, xt1, xt2 star. And here you have this star, if I put it here, star here plus here. So this will become e raised to minus j omega t1 minus t2 dt1 dt2. But this is the autocorrelation function. So suddenly we get 1 over 2t minus t to t minus t to t rxx t1 comma t2 e raised to minus j omega t1 minus t2. So notice this is t1 minus t2 dt1 dt2. And this is positive. Why is this quantity positive? Look at here. Don't lose track of this. We took a transform and took the absolute value squared. Then we divided by a constant. Expectation is multiplying by a density function, which is positive and integrating. So everything is positive here. This quantity is positive. Now, if the process has no stationarity, this is all we can do so far. You can, of course, push t to infinity, which we will do soon. But now I want to consider, how about, let's look at Whiteson stationary processes. Because the idea is, here is already t1 minus t2. So if I call this to be tau, and this becomes t1 minus t2, maybe we can simplify this. So if the process has no stationarity, this is the way you need to compute the power spectrum, and then you need to push the t to infinity larger and larger. And then you have to deal with each problem. But if it is Whiteson stationary processes, as I am going to show you, we can make some improvements. So let me copy the last line. So we have pt of omega is minus t to t minus t to t. Remember, I'm going to assume x of t is Whiteson stationary. As I said, if x of t is not Whiteson stationary, you deal with this equation, and then you put in whatever is the autocorrelation function, see how far it would go. That will give you and then you have to push the t to infinity, plus minus infinity. Where here this will become t1 minus t2 if it is Whiteson stationary. So this is rxx t1 minus t2. This becomes e raised to minus j omega t1 minus t2 dt1 dt2. So that means, once again, so notice if I call this to be tau, this is also tau. So we are integrating, we have done this problem before. We are integrating in this, this is t1, this is t2, and this is t1 minus t2 equal to tau. That's the new variable. So it looks like I can integrate on along one variable. The new variable is tau, because that's all it matters. dt1, dt2 is a small rectangle here. So instead of integrating over two variables, how do we did this? I did this for you earlier. So I take a small change in this is I take a small change. So in delta, this is, so this new line is t1 minus t2 equal to tau plus delta tau, or minus delta tau, I guess. And then, so we will integrate when the tau goes from tau to tau plus delta tau. We integrate over this integral, and then we push this tau from here to here, which is minus 2t to plus 2t. So this remember there is a 2t here, I forgot. So this is 1 over 2t. We'll get one integral, minus 2t to 2t on d tau. So I just need to compute this area. That area is area of one triangle minus area of a smaller triangle. So again, let's do this quickly. You need to find out the sides of the triangle. So how do we do this? I did this before for you. So look at this line. This line is t1 minus t2 equal to tau. So if I put t2 equal to 0, t1 is tau. So this point is tau, and this point is t. So this small distance is tau minus t. I hope you see this. This distance is tau minus t. So this distance is t minus tau minus t. So that is 2t minus tau. So that will be the side, because this is tau minus t, so is this one, tau minus t, and this is t minus tau minus t, because each side is tau. So the area of the triangle, the smaller triangle is base and altitude are the same, so 2t minus tau the whole squared minus half, you replace tau by tau minus delta, so 2t minus tau minus delta tau the whole squared. So notice the 2t minus tau will cancel off, then the middle term is going to be 2t minus tau multiplied by delta tau, and the last term is delta tau squared, which I am going to cancel. So this is the difference in the small area. So the function, which is rxx tau multiplied by that this quantity 2t minus tau delta d tau, that's it. Because then I push the tau from this edge to this edge, covering the triangle. Notice that if the tau, if the line is here, the tau will be minus tau and nothing will change. So I'm just going to put an absolute value here. And let me take this 2t here underneath here. So it becomes here. So the next line, this reads now minus 2t to 2t rxx tau. And in between, I forgot this factor. So there is also e raised to minus j omega tau here. So e raised to minus j omega tau. Then you have 1 minus tau over 2t d tau. This is positive. Why? Because look at the previous line. This is positive, so this is positive, this is positive. Finally, what am I going to do? So finally, I'm going to push t to infinity, so that in this case, we would be looking at the entire process from minus infinity to plus infinity. So notice that at this stage, I'm covering everything from minus infinity to plus infinity. I am covering everything this way also, over all realizations. All realizations, all time, for a Whiteson stationary process. So if I push t to infinity, look at here. Capital T is pushed to infinity, so this factor goes to 0. And so you get pt of omega in the limit as t goes to infinity is, look at here, you just get this term. And the limit becomes minus infinity to plus infinity. Minus infinity to plus infinity, rxx tau, e raised to minus j omega tau d tau. And this is positive. So I'm going to call this sxx omega. So because this is a, so this was the, if you look at our development, so this is like the Fourier transform in the deterministic case. See, this f omega squared is the energy. So we could think of this as this quantity inside as the energy due to this segment of the waveform. This is the average, I'm sorry, power, because we divide by 2t. So this is the average power. And then we simplified it over that duration minus t to t. Finally, when you push it to infinity, this is the power for the entire process, for the stochastic process. But this is something you are familiar with. This is just the Fourier transform, because look at the Fourier transform definition of any function. Function multiplied by e raised to minus j omega t. So power spectrum seems to be the Fourier transform of the autocorrelation function. We didn't assume this. That's the way it turned out. So this is known as the Wiener-Khinchin theorem. So let me pause here. Again, I don't want you to walk away saying that you take the autocorrelation Fourier transform, you get power spectrum. We didn't make any assumption. That's the way it turned out. It turns out that the, why do we call it power spectrum? Anyway, we do see that this is a Fourier transform relation. So if you remember, what is the Fourier transform relation? F omega is for any function minus infinity to plus infinity, ft e raised to minus j omega t. This is the Fourier transform. And the inverse Fourier transform is if you are given f omega, if you don't know this, you should review this starting now. This is the way you pick back the ft from f omega. So in our case, whatever is this function, I'll come into a second. We know that this function is non-negative because we have been following this. So the interesting thing is this is the Fourier transform of autocorrelation function that always turns out to be a non-negative function. In other words, if you plot it, it will never go negative. Now, since this is a Fourier transform relation, I can find this in terms of this function. So let me look at the inverse relation. So I get Rxx tau equals minus infinity to plus infinity Sxx omega e to the power plus j omega tau d omega 1 over 2 pi here. This is Rxx tau. So let me put tau equal to 0. So you get Rxx 0 is 1 over 2 pi minus infinity to plus infinity Sxx omega d omega. But this quantity is physical. This is expected value of x of t squared because that's the autocorrelation evaluated at 0. But this thing is the total power, right? Average mean squared power. You can see you are squaring the waveform and integrating. So what it says is, so first of all, if you plot this function, yeah, I'll rewrite it here. If you plot this function, first of all, we know that this function is positive. Remember what this function is. Sxx omega is Fourier transform of Rxx tau. I want to emphasize this. If you take Fourier transform of any ordinary function, you are not going to get a positive function. You'll get a complex function. But what we show is that, interestingly, if you take the Fourier transform of any autocorrelation function, that will turn out to be a positive function. It will never go negative, and it won't be complex. Moreover, we just said that if you take the area, this will be the total power. Then whatever this function is representing must be the power spectrum, because if you add up all the, so if the power spectrum is like this, that means this function has got a lot of power here. So we can call this to be the power spectrum because the total area represents the total power. So this is the power spectrum versus obviously omega, which is frequency. So now you can see the importance of Fourier transform. Now, so Fourier transform, which we have studied in, hopefully in some other course, all the properties we can bring it here to make all sorts of deductions. So that's a new tool you have. Now, if you are good at Fourier transform, that is good. If you are not good at, if you have never bothered to pay attention to Fourier transform, that is not good. So you need to go back and review Fourier transforms. I asked you to do that. There are lots of properties of Fourier transform. You have to, I'm going to give you some homeworks based on that. And maybe next test or the week after that, I will actually give you a autocorrelation and ask you to find the Fourier transform. There are several examples on YouTube solved by me on autocorrelation functions. So one problem now is, you can see, I'll give you an autocorrelation function. You need to figure out how to find the Fourier transform, because that's the way to find out power spectrum. So let's get this into, so power spectrum of a Whitening stationary stochastic process is given by the Fourier transform of its autocorrelation function. So this is the result here. So I'm going to represent it like this. For the Fourier, the power spectrum, which is non-negative, is going to be the Fourier transform of the autocorrelation function. So this is something you need to know, how to do the Fourier transform. because look at this. This is a Fourier transform. This is an autocorrelation function, e raised to minus alpha tau. So the question is, what is the power spectrum corresponding to? So you need to be able to do this and show that this is of the form alpha squared plus omega squared. How do you get this? So this is your job. I'm going to remember, you're all graduate students. I'm going to leave it to you to sort of get good at this.
Professor. So just wondering, we call this power spectrum because it's like we borrow a concept from electrical engineering, or is there actually any real life meaning? Like we take.
I mean, maybe you missed it. There is real life meaning. Look at here. So that's the. Hopefully, I looked at the inverse transform. You remember a couple of sheets back. Then I put tau equal to 0. So let's see. First, so I'll go to. We found this function. I don't know what to call it. So that's, we took the Fourier transform of autocorrelation function. So you agree that this is going to be non-negative? Yes, we proved it.
Yes.
Okay, so we don't know what the physical meaning of this is. So I'm going to do the inverse transform. Inverse transform is from Fourier transform properties. Inverse will be this function. Remember, in one place we are integrating with respect to omega. Here it is. So this is also true from Fourier transform properties. These two are Fourier transform pair. Now what? Now I'm going to put tau equal to 0 here. So I'll put tau equal to 0 here. Then I get this relation. Rxx0 is simply the area under this function. But this has a meaning on the left side. Left side is expected value of x of t the whole square. This is, this is the mean squared power. Because any waveform, square it through 1 ohm resistance, expected value is going to be mean squared power.
Yes.
So if you, what it says is, if you plot this, the area under this function gives you the total power. So what you see here must be the distribution of power versus frequency. That's why we call it power spectrum, not by arbitrary. You see it now?
Yes. Thank you, sir.
Yeah. So that's the whole point. So this relation is key. This tells you that this positive function actually has is going to tell you the power spectrum, the distribution of power versus frequency. Any other questions? So we can also prove the non-negativity of the, remember earlier we said R of T1 comma T2 is non-negative definite. We proved it a different way. Now we can prove it using the power spectrum. So we need to look at if the process is Whiteson stationary, then we want to show that R of Ti comma Tj is non-negative, I equal to 1 through n, j equal to 1. How do you prove this? So I'm going to Ti minus Tj. So this is going to be double summation Ai Then this I'm going to write in terms of the power spectrum, 1 over 2 pi minus infinity to plus infinity Sxx omega e to the power minus j omega. Instead of tau, I'm going to put T1 minus T2 d omega. So this you can write integral minus infinity to plus infinity Sxx omega. You have this double summation Ai, Aj, Ti, Tj. E to the power minus j omega Ti minus Tj and d omega. So I can, if you go home and simplify, you can write it like this. This double summation is, you can write it over one summation squared. d omega. See, everything is positive here, so you can see that if the power spectrum is positive, this will be a non-negative definite function. And the other way also, if this is non-negative, then this goes this way, and you can also show that this will be positive. So power spectrum is positive if and only if the autocorrelation function is a non-negative definite function. And now whatever the Fourier transform properties goes here. So for example, you remember Rxx tau has this property, Rxx star minus tau. So you can use this and try to get, and if the process is real, if x of t is real, Rxx tau is Rxx minus tau. So let's see what happens to Sxx omega is minus infinity plus infinity Rxx tau e raised to minus j omega tau d tau. So this is two integrals, right? Rxx tau cos omega tau d tau minus j Rxx tau sin omega tau d tau. Now look here, this is an even function given to you. If x of t is real, this is even. So this integral becomes 2 times integral from 0 to infinity Rxx tau cos omega tau d tau. Anybody knows this is an even function, this is an odd function. So what will be this integral? Anyone?
0.
Yeah, the second integral goes 0. So you get the property that Sxx omega, and this is an even function also. Everything is even here, the same as Sxx minus omega. So if the process is real, you expect the power spectrum to have real. So you should check into all this. I have my notes. And also I think there are a couple of videos I have on YouTube on also in the NYU classes on power spectrum. So you can look at that. All these things are there. And there are little more properties. So let me go to any questions? So this is what I am interested in. You have a system here. I have an input process White's and stationary with some power spectrum, some autocorrelation function. What can you say about the output? We know output is already White's and stationary. So this is input-output characterization. And this is where it's extremely useful because the system is like a filter. Any questions before I go in? So remember, this is easy to answer because if the input is White's and stationary, we already proved output is White's and stationary. And the cross correlation function, if you remember, is autocorrelation function convolved with h star of minus tau. And the output autocorrelation function is the cross correlation function convolved with h of tau. So if you want the power spectrum here, you just have to do the Fourier transform of this. That means, so what happens to a convolution? Here you have, so let me do that first. How do you convolve gt and h of t? So let me call this to be ft. So that's integral g of tau h of t minus tau d tau, right? That's what the convolution is. So let's look at f of omega, which is minus infinity to plus infinity, ft e raised to minus j omega t dt. Maybe you know the answer already. So ft, I'm going to substitute this g tau h of t minus tau. Then you have e raised to minus j omega t dt d tau. So this I can rewrite it as g tau. I'm going to introduce e raised to minus j omega tau. Here I have ht minus tau e raised to minus j omega t minus tau, because plus tau and minus tau cancels. And if I call this to be a new variable u, this is u, this becomes u also. So this is g omega, this is h omega. So you have the interesting property. So here it is easy, right? That the convolution results in product in the Fourier. So you have SYY omega is SXY omega multiplied by h of omega from this relation, just by taking the Fourier transform. Question is, what is the Fourier transform here? So let me write that. It involves this function. So remember, gt convolved with h of t. Here you have gt convolved with h of minus t. So let me do that too. Gt convolved with h star of minus t. I'm going to call this a of t. So a of omega is the transform of minus infinity to plus infinity a of t e raised to minus g omega t dt. So before that I should rewrite the, so a of t is how do you rewrite this? So this is h of minus tau star g of t minus tau, right? D tau minus infinity to plus infinity. So if I call g minus t to be, you can leave it like this is fine, or we can change it back. So if I call g minus t to be u, or I'm sorry, if I call minus tau to be u, notice this becomes h star of u, g of t plus u, minus du, and the limit will become plus infinity to minus infinity. So you flip it back, you get this. So, and I'm going to substitute this for a of t here. So capital A of omega is h star of u, g of t plus u, e raised to minus j omega t dt. This is in my notes and du. So this is h star of u, and here I have g of t plus u, e raised to minus j omega. Suppose I put t plus u, and this becomes e raised to, here you have e raised to minus j, so this should be plus e raised to j omega u. This cancels with this. Again, as before, this is a new variable, call it x, this is x. So this is dx, this is du. Here is a star, here is plus. So you can write one more line if you want. So I'm going to pull this outside, this star. I'm going to put the complex conjugation here. Remember, there is du here. So this star goes away, and here it becomes minus. But now this becomes simply, okay. So I hope you saw what I did. I pulled out the star outside, so then this plus will become minus. But this is simply h of omega star, and this is g of omega. So we get the result that the transform of these two is g of omega multiplied by h star of omega. So it's useful to remember that if h of t has a transform of h of omega, h star of minus t has a transform of h star of omega. I'm going to ask you to go home and find out the transforms of all this. What is the transform of h star of t? What is the transform of a time reversed signal, etc. All this is done. So if you time reverse it and take the complex conjugate, and you get simply complex conjugation in the frequency domain. So we can use this expression here. Here, so the answer is the cross spectrum is Sxy omega. Remember, the Fourier transform of this I'm going to call the cross spectrum is the Fourier transform of the input spectrum multiplied by Fourier transform of h star of t. I just did it here. H star of minus tau is h star omega. Now I'm going to plug this this expression here. So I get Syy omega. Before I do that, I want to say that this is the cross spectrum, and that doesn't have to be positive. Look at it. Cross spectrum has got a, this term doesn't have to be positive. This is positive. This could be complex. So cross spectrum could be complex. So what is the output spectrum? Instead of Sxy, I should put this thing. When I put this up, this becomes Sxx omega multiplied by h star. So that becomes h omega absolute value squared, again positive. So that's the key relation. So let me summarize it here. Look at the last line. The output to power spectrum is input power spectrum multiplied by transfer function squared. Any questions on that? So this is where it will begin to help us. You see, for example, this is an important relation. So I'm going to, so question is, how do you even pick up the filter? You have a stochastic process. Let's say it's a power spectrum is like this. So you can see in this frequency band is where most of the information about X of is related. Then think of this as the signal. And then you have, if you have a filter here, and if the filter, for whatever reason, let's say the filter shape is, so you can use the filter, so the output, call it y of t. What we have shown is Syy omega is input power spectrum multiplied by the system transfer function squared. This I just proved it for you. So if the system has some Fourier transform of, let's say it is a low pass function like this, h of omega, then your CC, if I apply this filter to this, you're only going to pick up this band. So if it is a band pass, it will pick up this. So the output will look like, will be 0, and then it will pick up whatever is this region, and then it will, so this will be Syy omega. So you can see that this is the advantage of a filter. You can use this filter to pick up and shape the input characteristics. That's where the first application comes in, even for, so just like in regular theorem, this is where the usefulness of stationary processes comes in. So for stationary processes, a lot of stuff we are doing can be, in the regular case, can be applied. Any questions? So your goal is, if I give you an autocorrelation function, you should be able to find it, the Fourier transform, and find the power spectrum. This is not an easy job, so you need to practice it out. Because when I give you a problem in 2 weeks, the only reason you cannot do it because you have never tried anything.
Professor, how to recognize the difference between this approach, the power spectrum, and the conventional frequency domain filtering?
Remember, in the conventional also this is true. If you have a function ft and you pass it through a function gt and you call the output to be at, then a omega is, of course, you know, is the f omega multiplied by g omega, right? But here it is different. I am not saying the transform of this is the transform of these two. See, that's not what we are saying. What we are saying is the power spectrum of the output is the input power spectrum multiplied by the transfer function squared. There is nothing like that here. Of course, you can square this here, each of them. But then whatever, so here you have even a basic relation. In the deterministic case, you can take the Fourier transform of each waveform. Here we can't take the Fourier transform of this. Remember, power spectrum is not the Fourier transform of the waveform squared. That's what first. Power spectrum is the autocorrelation. The power is the Fourier transform of the autocorrelation function. So you need to figure out the autocorrelation function, or you need to be given the autocorrelation function.
I see.
Right. So, in fact, the homework will involve some doing some of this. So, for example, how do you do this? Let's say this is an autocorrelation function. So this is an autocorrelate. Remember, this is a number, a carrier frequency. This is modulating this function. So what's your problem? Your problem is to find me the shape. How does it look? So do this. So you can say this involves some training. But if you are unwilling to do any work, why should I pass you in this class? So please do these problems, and also it gives you some understanding. I mean, you can walk out of this course with learning something to do. So I'll give you 2 weeks before I bring up problems like this. So I hope you know how it goes. Today will be, if you if you have done very well, you don't have to take today's test. Today is only a makeup test. So, so if you take today's test, then we'll give you, you would have taken 4 mini tests. And I'm going to take the best 3 for each of you and scale it to 35%. That will be your midterm score, and that will not change. So midterm is done with today. Then I think I will keep giving you, because I'll keep giving you problems like this next to 3 weeks, and then we will have a final exam. And again, I'll use some way of figuring out the best. I think that is 45 or something. And remember, homeworks count to 10. And if you remember, before all this mess happened, you have 5 or 6 quizzes. So I'll just average it and give you 10 points out of that, whatever you have done. That's how we'll decide. And so you can, and then you have on top of that the pass-fail option, whatever. So, but remember, you need to get through this course. You decide a minimum. If your total score is 10 points, how do you expect me to pass you, right? So whatever it is, you have to show me some performance to pass through this course. But I'm giving you as much detail. You're doing it at home. You're doing one problem at a time. And I give you plenty of time. So what more you want? You signed up for this course, so you need. It's my job to force feed you. Not force feed exactly, but sort of feed you something. Right?
So, Professor, so is the final going to be like multiple mini tests like we have in the midterm, or is that going to be a big exam?
No, remember. So I'll make it easier for you. I will keep going like this. So you will have mini tests next to 3 weeks. How many more weeks? I think 3 more weeks, right? Yeah, we have 3 more lectures. So I'll give you. Today is what, 16?
Yes, it's April 16.
Yeah, then we have 23, 30, and May 5 or something. We have 3 weeks, or May 9th or something. Then you have exam is on 14th, May 7th, right? May 7th is another lecture. So we have we have 3 more mini tests and then a final exam. Final exam, I'm not going to make you sit there for 3 hours. I'll just give you 2 problems or something. So it's like an extended minute test. So that way, most likely I'll get rid of 1 minute test. I'll figure out a formula to give you some advantage. But you have to practice and come. You have to solve problems if you want to learn something. So you can see I've been sort of asking problems similar to homeworks and so on from the course. And then that way, on 14th, I will have enough to give you a grade. And if you choose pass-fail, I'll give you pass-fail. It's very difficult. Usually, at this stage, let me put it this way. Unless you are completely responsible and, you scored really, really low, I don't see you should worry about failing. But if you refuse to do any work, then what do you want me to do? All right, so let me, so we have, what I have done today in the last 1 hour is a major topic in the stochastic processes, power spectrum. So we have to sort of go over it through examples and so on for you to understand. Just by learning the definition, you don't understand anything. By solving a problem, you will show some understanding. But let me go on and show you some applications and so on. Right. So I don't know whether you have heard about this process, white noise process. Maybe you have heard the term white noise. Remember, sunlight has got all the spectral components in equal behavior. So we define a process to be white noise by looking at its spectral characteristics. So if the spectrum is flat, like sunlight, white light, that's why it's called white. So so this is a white noise process. The spectrum is flat. Let me ask somebody, what is the average power of this process? Anyone? Hello?
0.
What is the average power?
1.
Expected value of WT squared. That's how do you express this in terms of the autocorrelation function? Anybody? Hello? I just went through this.
Minimum of T.
You are confusing it with the Wiener process. I'm just calling it white noise. Any stochastic process, let me call it X of T. So this is X of T. What do you call? How do you express expected value of X of T squared in terms of autocorrelation function? Anyone?
0.
Rxx 0. How do you express this in terms of the power spectrum?
The area under that curve.
Very good, right. So what I'm asking is, what is this average value for this power spectrum? Anybody?
Infinity?
Infinity, right, exactly. So what I'm trying to say, this is what we call white noise, but you can see this is not a not realizable because it's ideal white noise has got infinite power. So it's only an idealization. I want you to understand, when people say white noise, this is what they mean, but you cannot realize it because it has got infinite power. But what we can realize is a power spectrum like this. If a process has power spectrum like this, this is still flat, but in some frequency band. So if you call this to be white noise, what do you want to call this process? Anybody?
Pink?
What?
Pink noise.
Pink?
Yeah, I just guess.
Why pink? Why not blue? Remember, this still has pink, maybe just one color here, right? So it's more than pink. So we can call this, I forgot, what do you call it?
Color?
Yeah, colored noise, right. It's certainly not white, so you want to say some color. You want to call it pink? It's fine with me. So anybody, what is the autocorrelation function of a colored noise process? How do you find the autocorrelation function? Anyone? What do you do? Hello?
Do the Fourier transform to the
Inverse Fourier transform. You have to do Sxx omega e raised to plus j omega tau d tau. What will be the limits here? Minus b, not infinity, because the power spectrum is only in this region. Let's say it is 1, and this quantity is 1. So it's the 1 over 2 pi e raised to minus j omega tau over minus j omega. I'm sorry, minus tau, j tau, minus b naught to b naught. So the numerator is minus 2j sine b naught to tau over minus j tau. So minus j cancels. Here you have 2 pi, 2 cancels. So you get the answer to be sine b naught to tau over b naught to tau. So b naught over pi. But sine x over x is sinc. So this is b naught over pi sinc b naught tau. So that's the, so I want you to do things like this. So a colored noise has got an autocorrelation which is sinc b tau. So look at this problem. X of t is a zero mean Gaussian process. Can you read what I wrote? So what I'm saying is show that x of t, and I'm going to shift it by pi over b naught, let's say. I want to say show that these two, these two values are t1 and t2, these two samples are independent. So do you see, this is a problem. Do you see the problem? That the things like this could come up in an exam easily. So I'm saying x of t is a zero mean Gaussian process which has got colored noise within the bandwidth minus b naught to b naught. So its autocorrelation function is like this. So we want to, so let's find out the expected value of the sample at xt naught and xt naught plus t. These two, so this is the autocorrelation function as t1 minus t2, that is t. So that's going to be here. Rxx is here because a colored noise. It doesn't matter Gaussian or anyone. The transform, the autocorrelation is a sinc function. So this is b naught over pi sinc b naught to t. T is pi over b naught. B naught cancels. What is the value of sinc pi? Anyone? Sinc is sine x over x. So sinc pi is hello?
0.
0, right. So these two random variable, look at this, they are uncorrelated, but the process is zero mean. So they are also, no, I'm sorry, this is orthogonal, but the process is zero mean. So what is the correlation coefficient between these two random variables? Anybody?
Uncorrelated.
They are uncorrelated, but they are Gaussian. So independent. That's what you wanted to show, right? I hope you understand. So things like this, I could. This is a classic problem. So for Gaussian, what it shows is if you have a Gaussian process which is band limited, then if you sample it properly, you see you can put here multiples of samples. If you sample it properly, you can make the samples independent. So you see, this is telling you how to collect data. If you want to collect data independently from a Gaussian process, this shows you how you should sample. You cannot sample it too fast, but if you sample it at sort of this, you can think of this as the Nyquist rate also. So I'll do a stochastic version of the Nyquist problem maybe next week as an application. Any questions? What we have done just now? So you learned about colored noise, and so I hope you don't mix up with these are all three different ideas. You can have a Gaussian process, you can have it zero mean, you can have it Whiteson stationary, you can have the spectrum colored. Colored means like this in the spectrum. So if you have a process like this, so the theorem is, remember, a Gaussian process, it doesn't have to have any of these properties. It doesn't have to. It doesn't need to be Whiteson stationary. It doesn't need to be zero mean. It doesn't need to be colored. Colored means the spectrum is finite. But if all these are there and Gaussian, then we know that if you have a Gaussian process, if you sample it properly is what? Pi over B naught, then these samples are all independent. You can make the samples independent. I hope you see the result. But the Gaussian is important. Otherwise, you will be stuck with, for any other process, these samples will be uncorrelated. They won't be independent. But if you also want independence, then you need to have a Gaussian process.
Professor, on the previous page, how did you get the 0 at the last line?
Here?
Yeah.
What is sinc? Sinc is sine b naught x, b naught pi divided, no, b naught is gone, so sine pi divided by pi. What is the value of sine pi?
Oh, yeah, I see. Thanks.
So if the spectrum is like this, remember I went through this, the autocorrelation function will look like this, sinc. So anybody knows this relation? This is another Fourier transform property. You see, that's a fascinating result. What I'm asking is, if a time domain, this isn't time domain, okay, I flipped it. This isn't time, if this time domain has a transform of this shape, so time domain is here as sinc, has a shape of this way, and if I bring this shape into the time domain, what will be the shape here? Anybody knows what is the answer? I hope you see what I'm trying to write. Let me put it this way.
Is it symmetric?
What?
Is it symmetric?
What does that mean?
It's f minus x.
Minus x?
It's a sinc function.
The sinc is only an example. But first of all, variable is not x, omega, right? Is that what you meant? Hello? Look at what I'm saying. This, in the time domain, you have a waveform whose transform is capital F of omega. Now, so this is what I'll draw something arbitrary. Let's say this is a time domain, okay, somewhere here, ft. And let's say its transform is like this. I obviously exaggerate. This is F of omega. Remember, this is frequency domain. This is time. Ft has, now I bring in this waveform into the time domain, because this is in time domain. So this is capital of Ft. My question is, what will be the waveform here? What will be the transform of this waveform? Anybody?
F
So this,
minus omega.
what?
F minus omega.
Which F? Small f or capital F?
Smaller f.
Oh, so do you know how to prove it? So he is saying G omega is small f of what?
Minus omega.
All right, let's see whether he is right. So let's do the transform of, I want to do the transform of Ft. So that's minus infinity to plus infinity. I hope you can see, right? Ft e raised to minus j omega t dt. Okay. So I'm going to change this variable to, so this is, let me call this to be, this is of course g of omega, some transform. We want to find out what this is. I'm going to call it g of omega. This t has no meaning here. So I'm going to change the t to x. So I have this relation, g of omega is minus infinity to plus infinity ft. Let me do it here. So g of omega is what I want to find out. Minus infinity to plus infinity ft e raised to minus j omega t dt. So g of x is of course minus, I'm just changing omega to x. Ft e raised to minus xt dt. And this one I can write it as, I'm going to change t to something else. So fy e raised to minus j xy dy. Why am I doing this? You will see soon. Now what? Now I'm going to change y by minus tau. So wherever y is there, I'm going to change it. So this will become f of, what am I doing? Oh, hold on. Yeah, not y of it. I'm going to change y by t. I'm sorry, y by omega, in fact. So remember, y is a dummy variable. Y is only on this side. This is a function of x. So I can change y back to anything. I'm going to change it to omega. So this becomes e raised to minus x omega d omega. Now what? Now this is gx. But if you look at this, yeah, if you look at this, this is the, remember g omega is what we are interested in. And let me, for the time being, let me write, replace x by t again. So this becomes minus infinity to plus infinity f omega e raised to minus j omega t d omega. Now if I pull out, so this almost looks like the inverse transform, except there is a plus here. So I'm going to change omega to minus omega. Again, limits will flip and flip it back. So this becomes minus infinity to plus infinity minus omega e raised to plus j omega t d omega. But if I divide by 1 over 2 pi both the sides, this is just the inverse transform. So this becomes f of small f of t. What happened? So there, this becomes or the easiest way is you don't even need this. Here you pull out, so this can be written as minus infinity to plus infinity. I'm going to pull out a star outside. So this becomes f star right. Actually, you don't need any of this. This minus thing, you simply put this here with the minus t. So you are right. So this absorb this minus t here. So this is simply the Fourier transform evaluated at minus t. So you get this relation. It's going to be f of minus t. So you want a g of omega. So g of omega is going to be 1 over 2 pi f of minus omega. So you have to do some manipulation at home. So why am I doing all this? Yeah, so the question was, what was this thing? So the answer is what you said, a constant 1 over 2 pi multiplied by f of minus omega. I hope you saw this. So so that means whatever is this shape, it will get flipped and come over here. So you see, this is a fascinating theorem. If you take a waveform and find its transform, you get something. If you bring that shape into time domain, the shape is not this. Its shape is actually flipped version. So let's apply this to these results. We saw that the sinc function, did we see this? What did we see? Yeah, we saw that the autocorrelation function of a sinc function is this one, right? In other words, if we have colored noise, the autocorrelation function corresponded to be sinc b naught tau. Okay. Now I'm just curious. Suppose I bring this into the tau domain. What will be the transform using this property? Anyone? A waveform has some transform. If I bring that transform here, this waveform will get flipped. So what will you get as the anyone? Hello?
The same shape scaled by 1 over 2 pi.
Right, so you get the same shape. Can this be a power spectrum?
I don't think so.
Why not?
It should be positive.
Right, see, this function goes negative. So this cannot be a power spectrum. That means this cannot be an autocorrelation function. So I'm going to ask you certain things. So sometimes I'll ask you, you have to use this property. I'll give you some function. Let's say like this. Is this an autocorrelation? So is this an autocorrelation? So we know a rectangular waveform is not an autocorrelation. How about a triangular waveform in the tau domain? Anybody? Can this be an autocorrelation function? So you can use this test. One way to test is find its power spectrum, see whether it's always positive. So anybody remembers what's the Fourier transform of a triangular waveform? Hello? Anyone?
Sinc square.
Yeah, so how do you do that? So remember, triangle is obtained by what? Convolution of a triangle, a rectangle with rectangle will give you triangle. So now you can use the properties. The rectangular waveform has a sinc function, so its property is actually sinc squared, as you said. So that's positive. That means a waveform like this can be an autocorrelation function. So these things could easily come in a test next week or week after. If I give you a function, you have to decide whether it is an autocorrelation function or not. One property is you can try to do the non-negative definiteness using that matrix relation. Here is another method. So how about cos omega naught tau? Is it an autocorrelation function? I'm going to leave it to you. Sin omega naught tau. If you modulate, is it still an autocorrelation? So these are simple things. Look at this, say e raised to minus alpha tau. This is actually an autocorrelation function because if you go home and do it, this will come out to be this one. So this is like a low pass filter. What if I multiply that with cos omega naught tau? And also multiplied by sin omega. Which one is an autocorrelation function, etc. So I'm going to leave it to you. You need to, this may be there in fact in this week's homework. And also I could give you a power spectrum and ask you to find its. So if you do the Fourier transform inverse of a power spectrum, remember you get an autocorrelation function. So I can give you a power spectrum, for example, let's say omega alpha squared plus omega squared the whole squared. This is a power spectrum. I can ask you to find out this. So this is how we use ideas that you have already learned to enforce a few things here. Now, if you have never paid attention to Fourier transforms, this is going to be bad news because problems like a simple problem like this will come up in 2 weeks for you, and certainly in the final exam. So let's look. This is what the stock market guys do, right? They take a window. If they are here, they take a window, right? T minus tau to T plus tau. So y of t is T minus tau. T minus T, you go T this way, you go T this way, and average the process X of tau, d tau. These two are the same because you call this X. When X is minus T, you get capital T. When X is plus T, you get, when X is capital T, you get T minus T and T plus T. So that's, you can rewrite it this way, right? Either way you can write it. And so the question is, let's say I divide by 2 also. So this is stock market, you have seen it, right? 50 days average, 50-day moving average. So this is a moving average. As T moves, the window moves. So you will. So the idea is, if you have a process with a lot of variation, then the smooth process will be something like this. It will be less. It will be less zigzaggy. So if I define, if I define a process like this, you see, h of t from minus t to t, and you can see that I can write this as look at what I'm going to do. This is h of t or h of tau, right? So I can shove this in here, right? H of tau. There's no relation. So, but now you see this is the convolution of h of tau and h of t and x of t. So you can see this as x of t convolved with h of t. So this simple averaging process, you can write it like this. Remember, this is in the time domain. So what is the Fourier transform? So the power spectrum of the smoothed function, I hope you see this, is the input power spectrum multiplied by h of omega squared. What is the Fourier transform of this function? Anybody? If I have a rectangular window in time domain, go back to your previous course. Remember, there's nothing stochastic about h of t, it's just a simple function. What's the Fourier transform of this rectangular window? Anybody? Hello? We just did it a few minutes back.
Sinc function?
Yeah, it's a sinc function, right? Didn't we do it somewhere here? Yeah, I did it for you in detail, right? A sinc function has a rectangular window has a sinc function. This is not an autocorrelation function, just a filter. So this is sinc squared. So this is going to be sinc squared t omega. So look at what happens. So if you look at the power spectrum, suppose the power spectrum is like this of sxx omega, then the sinc squared is like this. So essentially, this is a low-pass filter, right? This is sinc squared. Depending on T, low-pass filter, this is your original stock, and it's actually mostly it's taking the whatever is happening here, it's taking the energy. So you can, what am I trying to say? You can think of the smoothing operation as a low-pass filter. Smoothing is the same as, I think you know that statement, right? Smoothing is the same as a low-pass filter. I just proved it for you, right? Because this is, most of the energy in the sinc is around this region. So this is getting multiplied by the power spectrum. So if the most of the things of the power spectrum is happening here, then you pick up this stuff. That's what the smoothing does. It sort of ignores the, because these amplitudes are below 13 or 17 dB down, I guess, these side lobes. Any questions? So that's smoothing. Now I want to talk to you about the power spectrum for discrete time processes. Any questions before I do that on the smoothing? So there are some very difficult autocorrelations that I have found the answer, not that difficult, but a little, so you should go through, I think I have 2-3 lectures on Fourier transforms and power spectra on YouTube, also maybe on NYU classes. So I'm going to take some problems from there and put it as homework. So you don't have to kill yourself, at least look at the methods used. And simply don't try to copy the answer, because try to learn the techniques so that if I give you a problem which is similar to that, you can do it in your exam. As I said, the whole idea is I want to get you out of this course with some knowledge of the course. And just by reading it or looking and watching a video is not going to help you. I mean, it will help you a little bit. But the idea is then you use that knowledge to do problems. That's when the ideas go into your head. So that's why the tests are designed to do a little bit thinking. Now, I want you to realize that you cannot skip this topic, because this is a lot of things in a stochastic process are looked through the power spectrum. So autocorrelation is the key because the Fourier transform of the autocorrelation is the power spectrum. So you need to relearn all the properties and tricks of the Fourier transform so that you can use it to solve problems here. See, it doesn't make any sense before you come into this course or even before the midterm if I tell you that a Gaussian process, so long as it's band limited in the spectrum domain, if you sample at a certain rate, you can make the samples independent. Why will it make any sense without this course? Any questions? Otherwise, I want to do this quickly for a discrete time process. So remember, a discrete time process it's only defined for discrete values. Like you may have different but you only are defined at these values. So x of n, you may get it from sampling a process, and its autocorrelation is, remember, R of x of n comma m is expected value of xn multiplied by xn star. And this is Whiteson stationary if this is a function of n minus m. So I'm going to look at Whiteson stationary processes. So then you can write it, and let me call this to be R of n minus m. Then you can write R of tau in terms of this way. Because R of tau is only defined at all these places, autocorrelation functions. At t, 2t, 3t, etc. So if you want to write it as a continuous function of tau, I can using this. And then we use the property that the power spectrum is the Fourier transform of R of tau. So Sxx omega is the Fourier transform of R of Rxx tau, which is summation Rk delta of tau minus kt e raised to minus j omega tau d tau. So this integral, as you can see, this will turn out to be sigma Rk e raised to minus jk omega t. Sometimes t is suppressed, t from minus infinity to plus infinity. So for a discrete time process, you end up with, you can come up with the DTFT, discrete time Fourier transform, gives you the Fourier. So again, RKs are the autocorrelation functions at wherever you are sampling. But this power spectrum is repeats, right? Because Sxx omega is the same as omega plus 2 pi over t. Right? So it will repeat from minus pi to pi if t is 1. Otherwise, minus pi over t to t. So for a discrete time process, it's enough to look here because this information is the same. All right, so all this brings, I will do one more thing, then we will stop, I think. So this is a big topic in filtering, match filter. Now you have enough background to learn about match filtering. So I'm going to take 2 minutes, 1 minute break, and we should be done by 5:15 with this. If I don't complete this, we'll do it next week. Let me start this now anyway. Any questions? Hello? I'll do the match filter for a simple case today. Then you think about it, then we'll do the complete case next week. Now we are on to some practical problem. Anybody there? Hello? Any questions? Tell me. Hello? Anyone there?
Hello, Professor.
All right. So, you have any questions?
No, not that I'm concerned with right now.
All right, very good. So, let's look at this problem. So, signal is contaminated in noise. So, I hope you can read. Maybe this pen is bad. I hope you can read this. Right? So, a signal is contaminated in noise. What is the best filter to use to recover the signal? So, we are, as I said, we are on mainstream problems. So, think of this as this is what you transmit. And on top of that, now assume the noise is riding on top of this. So, this is what you are getting. So, you want to pass it through a filter and you want to sort of recover something. This is the, how do you do this? That's the question. So I'm going to call the output here as a signal part and a noise part. Noise I'm going to call W of t. So anybody, how will you get the signal part? We just went through this. Just a signal. Signal is deterministic signal. There is nothing, it's a known waveform. Usually in a radar, you transmit a known waveform. What is coming back is contaminated noise, contaminated waveform. So you want to, even in communication, you know, you are transmitting a BPSK signal most of the time, or QPSK, or 16 PSK, whatever. But during each symbol duration, it's going to be either a +1 or -1. So the wave, and you know the wave shape of the waveform. You just don't know which. So at least if you can figure out the shape there, then you can easily see whether it is +1 or -1. So the problem we are looking at is the signal is deterministic. So this signal is going to be the convolution of S of t and H of t. So this is also deterministic, whereas noise is a stochastic noise. So the noise component is N of t convolved with H of t. This is, remember, we went through this. A stochastic signal applied to a system gives you stochastic noise. So what, see, remember, we want the best filter. So question is, what is best here? How do you pick up? So a best filter, that's the job. So what I'm going to do is, so again, think of this. This is a deterministic. This is stochastic. So we have a mixture. You can have stochastic signal in stochastic noise, like in a submarine. A submarine, there's a fan there at the bottom, right at the back, that moves in the water, generating a quasi-stochastic signal, right? The fan is rotating, but interacting with water, turbulence, and this and that. and somehow that's the signal you pick up using hydrophones or something. So that's not music, but that's a stochastic signal. And on top of that, there is more noise in the underwater ocean. So that's so that's not the problem we are looking at. We are looking at communication or radar problem, where a known signal is corrupted by noise. So you can see the best filter somehow should use the known signal. So the question is, what is the best filter? So what do you mean by best? That's the thing here. So we will use the signal to noise ratio at the output as to define the best. So signal to noise ratio at the output is, in the signal to noise ratio. So the output you have W2, which is stochastic, output noise. Where is it? Here, output noise, stochastic. So its power is, remember, all that makes is you can talk about this quantity, average power, average noise power at the outputs. So you may say, why don't you do the same thing at the input also? First of all, input is it's not a stochastic, I mean, the signal is not stochastic. And you are going to make the decision, let's say at some time instant t equal to t naught. So you will see that what makes sense is this value should be as high as possible. So I will make it square of the energy. And I want to maximize this quantity by designing the filter. This is I hope you understand my criterion. It may sound crazy, but this is what is universally done. So the rationale here and here are different. It's like you are dealing with the milk and water. One is stochastic, this is not stochastic. So I'll write down in the next sheet. So SNR output is average noise power, average output noise power. So somebody cleverly thought about this, and here instantaneous output power at t equal to t naught, because a decision is made This is like saying if you are going to go out for a date in the evening, why wear a suit and tie when you go to bed? So what you need to do it only at that time, right? So what am I trying to say? The SNR output you want to maximize only when you make the decision. When you make the decision is you are only going to look at the output power at t equal to t naught. So that's going to be output to value. We are going to square it because plus minus shouldn't matter. Whereas here the average value of the output noise. But the denominator is, we know this is RWW0 divided by S hat to t naught squared. So this is what we want to maximize this. So maximization means hopefully the numerator is going to be maximized and the denominator is going to be minimized. But RWW0 we can write in terms of its spectrum, right? So that's the whole point. So SNR output is the denominator is 1 over 2 pi minus infinity to plus infinity S omega omega d omega, right? Because this is any spectrum area under the spectrum is the total power, right? With a 1 over 2 pi. And here I'm going to write in terms of its inverse Fourier transform. So this is S omega e raised to j omega t naught d omega squared. So notice here, this is S hat of t. I wrote it in terms of its transform. So ST has a transform of S of omega. So if ST is a pulse, the transform is a single waveform. This is in the frequency domain. This is in the time domain. But look at here. The WT is NT. So we learned earlier, right? If two signals are convolved or a process goes through a noise a system, then the output power spectrum is input power spectrum multiplied by system squared. So this quantity in the denominator is input to noise spectrum multiplied by h omega squared d omega. By the way, I made a mistake here because this is the output to signal, right? This is the output. So this is the output to transform. But output transform is input transform multiplied by h of omega. So the numerator is input transform multiplied by h of omega e raised to j omega t naught d omega squared. And 1 over 2 pi here, squared here, so you get this expression. Now I am going to take the noise to be white noise today. Tomorrow, next week, I'll do non-colored noise. That means this quantity is a constant, sigma squared. So I'm going to pull it outside so that this expression becomes 1 over 2 pi sigma squared, and I have h omega squared d omega, and here s omega h omega e to the power j. So question is, I want to get rid of, I want to maximize this expression. This is SNR output. I want to maximize it on capital H. Capital H is the filter that we don't know. We are trying to find out the filter. All right, so then look at the numerator. Maybe I'll give you a proof next time. So if you have two functions like this, you can use, you might have seen this result. This is true in the frequency domain or time domain. So if that is true, I can simplify the numerator here. So SNR output is less than or equal to 1 over 2 pi sigma squared. The numerator becomes the product of these two. So I'm going to call this to be one function. Keep that in mind, s of omega. So that's going to be the square of that, which is going to be s omega squared d omega. Here h omega squared d omega. Here you have h omega squared d omega. This cancels. And this is simply energy of the signal divided by sigma squared, because you simply have s omega squared d omega 1 over 2 pi by sigma squared. So this is the max. This must be the maximum value of SNR. And you get the maximum, as you know, you get equality here if these two quantities are proportional to each other. That means these two quantities are proportional. That means h of omega is the star of s omega. I'll do this again next week. So this is s star omega e to the power minus j omega t naught. Now I'm going to leave you at home. You go and try to find the inverse transform of this. You need some exercise also. And that will give you the filter to be s of t naught minus t. In other words, if you find the transform of this, that will turn out to be s star omega e to the power minus j omega t naught here. So remember, these are all new to you. So we found the filter. So what it says is the filter, the best filter depends on the whatever signal you are on the transmit signal. So if the transmit signal is like this, for example, okay, let's say this is the way the transmit signal is. Look at what the, so first you flip it. That means you flip it in time domain. So it goes like this. Then you shift it by T naught. So then it goes so this is ST naught minus T. So this is the match, this is your receiver. And we call it matched filter because it is matched to the best filter is matched to the transmit signal. Did you understand all this? Anybody? Everybody? This is also there in my notes, I think lecture number 18. It goes in detail. And I think on YouTube, there are 2 versions of match filter. Both are very popular. I think it has got 8,000 or 9,000 hits already.
Professor,
Yeah.
is there a way to know if the assumption made about the noise is the best model?
What assumption did I make?
For example, when we assume the noise to be the white noise?
All right, so that I did it a special case today. As I said, next week I'll do you, if you don't like, I'll do the general case when the noise is not white.
So there is a way to determine if this is the best model for.
Yeah, right. And so if the noise is not white, we have to talk about something called a whitening process. I'll describe it next time.
Okay, thank you.
Right. So that's a problem. So we can, here is another problem for you. So this is the power spectrum of noise. So obviously this is not white. Question is, can I design a filter? This is for next week, so that the noise at the output looks white. Noise here, white noise. Question is, can we do this? So if we can do this, we call this the whitening process. We'll talk about this next time. This is like laundry. You wash the clothes to make it white. So this is called the whitening procedure. How do you whiten a noise? So you clean it by passing it through another filter. How do you find that filter? So that's so these are all new problems that obviously you haven't seen before. And so to end, who asked me that question? Hello, what's your name?
Professor, I'm Zach.
Okay, Zach. So to answer your question, you can see this is what I'm going to do next week. If the noise is not white, I'll design a filter which will make the noise white. But you may say that looks stupid, but at least you can see. Then I'll pass the signal also here. So signal will go through GFT. You'll get a new signal in white noise. Then we can use what we learned today. So 2 filters, whitening filter and match filter will do the job. Do you see this?
Yes. But
So this is done universally. What I just told you is always done. If the noise is not white, whiten it. Then you know how to take care of white noise. So you design the match filter for a white noise. When you couple these 2 steps, you can solve all problems. Every problem is solved just this way. In communication, all the problems. If the noise is not white, first remember when you whiten one, you also wash the baby. The signal also gets transformed, but you can track it. And then you design a match filter to the new signal. In other words, conceptually, let me solve your problem here, but we'll go over detail. A signal is coming in noise, but this noise is not white. It has got some spectrum, not white. So first I will design a filter. I don't know how to do it now, so that the new noise that is coming out is white. but this is white noise. But in this process, the signal got transformed also. It became S tilde. But you know, S tilde is just ST convolved with GT. So if you know this filter, you can find this. Now I know I can just design a match filter, what we learned today. This is going to be S tilde of T naught minus T is this filter. So the whole operation is, to answer you, you put these two together. Do you see it?
Yes, I see.
All right, so that's the end of story for all problems. Everything else is detail. How do you design that filter, realizable implementation, all that stuff. But conceptually, the theory is, so again, let me tell you, whitening followed by match filter is the best filter everywhere. But nowadays, you just deal with the problem by problem. So the match filter is for white noise. So please read through all this stuff, solve some problems, solve the homeworks. I'm going to think about how to give you some homeworks today. And then we will go from there. Any questions? We have a few minutes now before the exam. Sushant?
Yes, Professor.
So what time, Heifeng is there or no? Heifeng?
Yes.
You, what is it? The exam is set for time release at 5:15?
5.
What is it?
It's like 10 minutes. We could send out the mails early also.
You can send it out if you want, right?
Yeah.
Yeah, let me finish talking. Hold on. Anybody has any questions? Remember, this match filter is, if you go into any engineering design, especially communication, this is a concept you should know well. So I'll go over it again. There is a lot more to this, but at least I want to give you the, so match filtering white noise is what first you study. Then we deal with how to take care of colored noise. Then you can combine, then you can be clever enough. You don't have to do it in 2 steps. You can, remember, after all, you learn this. If you have cascade of 2 filters, you can combine it and you may be able to simplify it depending on, sometimes the poles of this and the zeros of this can cancel out, giving you a simpler filter depending on the problem. So you can make use of a lot of results. So that's how you expand your horizon. So you're learning certain things new, but these are key concepts here. Whitening, concept of whitening. It's the same as laundry. Something is not clean, you make it white. White is, of course, here we mean white color or white spectrum, which is all the colors are present, or spectrum is flat. I mean, I can go on, but I want to give you some time. Then also there are ideas on transmit signal design, etc. I don't know how much I'll go, but next week I'll again start with white noise, and then go into maybe some signal detection in problems and so on. So we have 3 more lectures. So all these things are going to be now applications of whatever we have learned. I'm going to spend a little more time, maybe 1 more lecture on power spectrum and so on. And if I get enough energy, last time nobody came. I mean, I don't want to give Saturday or Sunday lectures when you don't show up. So I was very disappointed. Only 20 people showed up. So I'm not going to bother with, I was going to talk about Fourier transforms, but if you don't show up, I don't need to lecture to myself. Otherwise, I would have, I lost enthusiasm when I saw that nobody's coming. Anyway, so it's 5:05. So Sushant, if you I'm not, what time did you, why don't you set it up for 6 o'clock and we'll sharply cut it off at 6.
I put it as 6:10.
Okay, 6:10 is good. Why don't both of you can send them the exam now? And no, hold on. Everybody has to open the cameras, please. I don't want to go through this. Open the camera, then I'll give you the exam. Okay, just quickly go through and see whether everybody has opened the camera.
Yeah, almost.
Who?
There are some people left.
Okay, please open it up. You're wasting everybody else's time. Lou, why you young Lou? Jinghuan Wu? Sinyu, Zhang? Oh, it looks like everybody is on. Is it?
No,
Why not?
there's some
There-
students.
There are 10 students left. 9 students.
All right, so hello, those of you, please open the video so that we can send you the exam. You're wasting everybody else's time, please. Okay, tell me, Sushant, when they're ready.
Yeah, switch on the camera, everyone.
Remember, you are losing time unnecessarily. Zuwu, Siwu, Hifeng,
Ah,
call those guys. Maybe send them an email to
okay.
Kang and ask them to open the camera.
Jingwon Wu, Zi Wu, Zhongxiu Yang,
Only 3 of them, right? 4.
Jiachun Wang.
Jianlun Wu, Zong Yang, Song Yu Yang.
Yeah, only 2 of them left. So yeah, sending out emails.
No, let them open it. That's crazy. Why you okay, you send it to them, right? And note their names. Maybe we'll do something. Sushant, you send it to them?
Yeah, just now.
Hmm?
Yeah, I did just now.
Okay.
Professor,
Hmm.
I didn't receive the question.
What's your email?
4AQ489.
This
Yeah, I haven't received the
No,
question.
there,
I didn't
there,
receive it.
there's one student who do not open the camera.
who is this? Yang? Y-A-N-G. Why don't you send him any? First, send him an. Can you put your email in the chat? Hey, Sushant,
Yes, Professor.
send him a. Put your email.
No, I think Hefeng didn't send the question paper. So.
Hefeng.
Yeah, I send now. Yeah, I send.
Okay, everybody has questions now?
Yeah, they got it, yeah.
All right, keep an eye on everyone.
You have time till 6:10 to upload it.
What is it?
No, they have time till 6:10 to upload it.
What time is it now?
5:13.
Yeah, remember, you're almost an hour. You don't need an hour. It's two simple problems. You need to, if you want to get full credit, not only show the density function, show the regions, draw the diagram of joint density function valid, etc. Remember, people who got 10 out of 10, you don't have to take this test.